they had to cook up like Breaking Bad, like Heisenberg. They had to cook up the material that actually went into the thing itself, the chip itself, that is being now used to do this process.
Yeah, exactly. It's like completely novel.
It's not like you can just go like, hey, NVIDIA, like, hey, you know, TSMC.
No.
And then
they were doing it. So quantum computers, right? The promise is to break encryption, simulate materials. And making a quantum computer, as of now, it's still a hardware problem.
Okay.
Okay. It uses a qubit instead of a classical bit. So a classical bit is your transistor. So that's my 0 and 1. A qubit can be in a superposition of two states. You can do a lot of things in parallel. And you can access a lot of computational stuff in parallel. Yeah. The key bottleneck is the following, okay? In a transistor, if I turn it off, it's going to stay off. In quantum mechanics, that's no longer the case because these qubits are made out of incredibly small technologies. Okay. And so there's a lot of forgetting that happens. Let's take the extreme case of an electron that's spinning in one direction, and that's my 0. If it spins in the other direction, that's my 1. Well, I need this thing to remember that it's spinning in that direction.
Yep.
But if there's a bunch of stuff around it, it's going to start poking it, right? There's a bunch of little magnetic fields that the atoms create that are going to try to change the way that my electron is spinning. So it's not going to take very long for that electron to just get influenced and forget that it was a 0 in the first place. This is called the decoherence time.
Okay.
And one of the central challenges in creating a workable quantum computer is to make the decoherence time way, way longer than the algorithm time.
So the point is, you don't actually have like a workspace that is active for long enough for you to do like valuable computation.
Yeah.
We're at a scale now where the little stuff changes in very, very, very small things that might not have mattered in a classical system. Matter a lot in this quantum system.
So there's different kinds of qubits. One that we're talking about is actually pioneered by the 2025 Nobel Prize in Physics. And IBM and Google now use something called the transmon design. It's basically their design, but they've attached a large capacitor on the side.
Okay.
And they've made it insensitive to charge noise. This new paper, they're getting their stuff all the way to milliseconds.
Okay.
And this is a victory against the materials that we're using to actually create that transmon qubit. And this millisecond timescale is about 3 times the timescale that was there before, the record.
Got it.
And it's 15 times the industry standard.
Okay, got it.
It's multiple groups in the university. The chemistry department was involved. The electrical engineering department was involved in this ecosystem at Princeton to create this qubit. And this qubit is amazing.